Swayam Prabha. Digital India. Educated India.
My name is Saravanan Vijayakumaran. So I'll be giving a few lectures on blockchain. I'll be starting with Bitcoin, the first blockchain. So what is Bitcoin? When you hear the word Bitcoin, it means many things. Firstly, it is a cryptocurrency, but it also refers to an open source software which you can download on your computer and it can run. And it also refers to a decentralized network. And what do I mean by a decentralized network? A decentralized network is a network like this. So these circles here, they refer to nodes. Think of them as computers which are running the Bitcoin software. And these edges between these circles, they refer to network connections. So by decentralized, I mean that there is no central coordinator. It is each node is equal to the others. So what is the cryptocurrency transaction workflow? So here's a picture. So here there is a party, Alice, who is trying to who wants to send some Bitcoin to Bob. So the first step is that Alice will request Bob's address, and then Bob will send this address to Alice, but this will happen off chain, that this sending of the address does not use the blockchain. It can be through email or WhatsApp or some messaging service. And then Alice will transmit a transaction which will send coins to Bob's address. And when she transmits it, she'll transmit it on the cryptocurrency network. And eventually, this cryptocurrency network here, which is a decentralized network, the transaction will propagate throughout the network. And when Bob queries for the transaction, he will find that payment has been made. So when you have a decentralized network, there is an issue of there are several issues. The first issue is counterfeiting. So how do we know that a particular coin is valid? So in India, we have the RBI, they will print currency. So they have a lot of anti-counterfeiting measures in the currency. But when you have a decentralized network where nobody is in charge, how can you ensure that people cannot create coins out of thin air because nobody is in charge? The other is how do we decide the currency creation rules? Because again, nobody is in charge, so how do we enforce that only a certain amount of currency can be created? Because if we create too much of the currency, then it will become useless or it will not have any value. So we need to limit the amount of currency which is created. So then who will decide that and how do we enforce those currency creation rules? That is the second challenge. Third challenge is double spending. So let me illustrate double spending with an example where Alice is going to pay Bob some digicoins for a cake. And Alice uses the same N digicoins to pay Charlie for a book. So I have a picture here. So here Alice is the person who's trying to double spend her coins. So you have a decentralized system again where the transactions will be propagated. So first Alice signs a transaction or creates a transaction which pays Bob N coins, and then she makes a copy of that coins because they're digital coins, and she sends it to a part of the network which she knows that Charlie will query. So in this picture, I have Bob is querying this part of the network and Charlie is querying this part of the network. Somehow, let's say Alice has this side information. She knows where where Bob and Charlie will query their networks. So Alice makes 2 copies of the coins and she sends it, and Bob the baker will give her the cake. And if she can do this copying before the network propagates the transaction, both the transactions, and detects some contradiction, then both Bob and Charlie would have parted with their goods, which is the cake and the book, and Alice would have double spent. So this kind of double spending problem does not exist for fiat currency or real currency, because if I have a 100 rupee note, once I give it to a vendor, I can't make a copy of it. It is unique to digital currency. So how do we solve this double spending problem? I said digicoins and not Bitcoin here because Bitcoin has a way of solving this double spending. So we'll see what that is. And we want a solution without a central coordinator, because if there is a central coordinator, then the central coordinator can just maintain an account and they can ensure that the coins are not spent twice. So how do you avoid double spending in a decentralized system? So this double spending is familiar to academics. By academics I mean like professors and PhD students and so on. So sometimes we submit the same paper to 2 conferences. Again, a paper is a digital asset, so you can just make copies of the PDF and you can send it to 2 conferences. This practice is frowned upon, that is, it's not considered good because conferences don't want to accept a paper and realize that it has been accepted somewhere else. One possible solution is that the reviewers who are reviewing those papers, they can Google the paper contents to find duplicates, but that solution fails if the conferences are accepting papers at the same time, and or if the conference proceedings are not published. You can Google only for information which is on the internet, but some conferences may not publish their papers, so then this cannot help. So a better solution is to have a single public database where you store all the submissions to all conferences. It's a hypothetical solution, but this is one solution. So what Bitcoin does is the same thing. So it has a single database, and that is called the blockchain. So the blockchain in the context of Bitcoin is a public database to store all transactions. So this public database will be used to detect double spending. So if all the transactions are stored on a single database, then we can query the database to check if the transaction has been has already, or the coins have already been spent or not. The other thing about this the Bitcoin blockchain is it is replicated by many network nodes. So there we want a solution without a central coordinator. So this is the what we want is that this database should be replicated by many network nodes. So the blockchain itself is looks like this. So I have just a illustration here. So these rectangles are blocks. Block 0 is called the Genesis block. I think it was January 2009 if I remember correctly. Each block has a block header and a list of transactions. The significance of the block header we'll go into in some time. And these blocks are linked. I am showing like a dotted line here. I will describe the exact specification of how the blocks are linked, but this dotted line is the chain part of the blockchain. So you have block 0, then that is block 1, the next block is block 1. So blockchain in the context of Bitcoin is a linear list. It is not, it cannot have like a tree structure. It has to be a linear list of blocks. And today there are more than 760,000 blocks. So block 0 was 2009, January 2009. Now today about more than 760,000 blocks have been created. So we'll go into these details as we go along. But how are these blocks linked? So I said there is a dotted line here like linking. So how are these blocks linked? So this is, I have expanded the fields in the block header. So there are multiple fields. So this is the block header which I showed in the previous slide, and then I have a list of transactions. So let's look at only the block header which I have expanded. So there are a bunch of fields here, then there is a version number, there is the hash of the previous block header. Now this, what this hash is it's the output of a cryptographic hash function. And then there is also some hash of the transactions and some other fields which I will explain later. So what we are asking is how are the blocks linked? So the linking of the blocks happens through this second field which is the hash of the previous block. So here in the previous slide I had some phrases here. I have replaced them with variable names. So these are the variable names in the in Bitcoin core, which is the reference implementation of Bitcoin. So Bitcoin core is written in C++, so these are all C++ variable names. So the prefix n stands for integer. The prefix hash is a hash output of a hash function. So except these two fields, hash previous block and hash Merkle root, everything else is an integer. And I have given some field sizes, 4 bytes, 32 bytes, 32 bytes and 4 bytes and so on. So this hash previous block is how the blocks will be linked. So what will happen is that you look at the previous block header. Now there is only one previous block because I said the Bitcoin blockchain is a linear list. So there is a single previous block header. You hash that previous block header using the SHA-256 hash function twice. That is, you hash it once and take the output of that SHA-256, hash it again, and you the output of this turns out to be 32 bytes. So that is inserted in this hash previous block. So that is how the linking happens. So if I know the current block header, there is a unique hash previous block field which is the double SHA-256 hash of the previous block header. So that is how the linking works, and we will see the reason for this linking when we discuss Bitcoin mining. So what are cryptographic hash functions? So they are functions which are easy to compute but they are difficult to invert. So they are like one-way functions. You can go in the forward direction very easily but difficult to invert. Then they are collision resistant. If I have two distinct inputs to the hash function, cryptographic hash function, then it's very unlikely that they will have the same output. And the outputs of the cryptographic hash function look like pseudo-random outputs. They are not random because for the same input the cryptographic hash function will always give the same output. So it's pseudo-random in the sense that the output looks like it has uniformly generated from the space of outputs. So SHA-256 is a specific cryptographic hash function. CHF stands for cryptographic hash function, which was approved by this National Institute of Standards and Technology. So NIST is a American organization, government organization, which does standardization of various things including cryptography. So they had a call for hash functions, and then they selected a few hash functions which satisfied their criteria, and they approved this. The SHA stands for secure hash algorithm, and 256 indicates that the output length is 256 bits. So hash functions typically have fixed length outputs. So the output of SHA-256 is always 256 bits. So here I have an example of some input output pairs. So I have just hashed the inputs December, so DEC0 to DEC9. This is the input to the hash function, and in each row I have indicated the output of the hash function, output of SHA-256 specifically. So the output is 256 bits, but I have used hexadecimal digits to represent the 256 bits. So 4 bits is one hexadecimal digit, so there are 64 hexadecimal digits in each row. So as you can see, even if I am changing just one character from DEC0 to DEC1, I'm just changing one character, but the output looks very different. There is nothing you can find common. Similarly for the other outputs. So, and the thing is that the space of possible outputs is very large. So the space of possible outputs is 2 raised to 256 because the output length is 256 bits. And even if you were to do a billion hash computations per second, it would take 78 billion years to calculate 2 raised to 100 outputs. And this is an extremely small fraction of the total space. So this 2 raised to 100 is what fraction of the total output space? It will be 2 raised to 100 divided by 2 raised to 256, that is 2 raised to minus 156. It's a extremely negligible fraction of the total output space. So you cannot exhaustively compute all possible outputs, and that's why I said it is difficult to invert. So for a given input you can calculate the output very quickly, but if I give you only the output, it is very hard to find an input which matches this output. So let me explain hash cache as a prerequisite to describing Bitcoin mining. So we have a public database, and if you have a public database, then there is a problem of spam. So every one of you owns a database where anyone in the world can add entries, and that is your email inbox. People keep sending spam emails to your email. So hash cache was proposed in 1997 to prevent spam, and it uses this following protocol. So suppose an email client wants to send an email to an email server. The email server could be something like Gmail or Hotmail or Yahoo. Now the client and the server, they will agree upon a cryptographic hash function. It can be SHA-256 for example. The email server will send the client a challenge string C, and the client needs to find a response string R such that the hash of C concatenated with R. So this symbol here, double bar, means concatenation. So the hash of the challenge string concatenated with the response string should begin with some k zeros, where k is some positive integer. So the protocol looks like this. So first the client will say, I want to send you an email. It tells the email server, I want to send you an email. Then the server will say, okay, here is a challenge and here is an integer k. So the client will do some work, and then it will search for a response string R, and it will send that response back to the server with an email it wants to send it, the server. Now the email server will compute the hash of the challenge concatenated with the response and check that it begins with k zeros. So how does this prevent spam? It cannot prevent spam, but what it does is it bottlenecks spammers. So what spammers typically do is they run a script and they have a advertisement for some shady products, and they just broadcast it to everybody they can, whoever email address they have harvested. But if suppose before sending every email, the email client has to do some work, then that will create like a bottleneck. So let me show you a demo of this. So this R is considered proof of work. It is difficult to generate but easy to verify. So let me just quickly show you a demo of how that will work. So I have a Python script called hashcash. I'll show you the script, but before that let me invoke it. It's so this hashcash has a single function whose usage is like this. So this hashcash function will take 3 arguments. It will take a challenge, the C which I showed in the previous slide, then the number of trials, so number of times I want to try some finding the response, and then the number of zeros, the K, number of zeros the hash output should start with. So let's try that. Hashcash, let's say ACM, and let's say number of trials is 10 and I want it to start with 4 zeros. So what this script does is it computes the SHA-256 hash of the string ACM concatenated with 1, 2, 3 and so on. So R, the response string, it's choosing as the integers 1, 2, 3. So it computed hash of ACM1, it got 6, 5. So this does not start with 4 zeros. So 4 binary zeros is 1 hexadecimal 0. So if you notice the last output, this starts with 1 hexadecimal 0. So that's why it stopped. So the hashcash protocol says that the concatenation of the challenge and some response can be anything, should start with some k zeros. The hash of that should start with some k zeros. K was 4. So it tried 5 values and it stopped when it found ACM5. Now this h is my hash function I have stored there. So now if I hash this ACM5, then I get the same output as here. So why am I showing this? So verifying the output does not require me to do 5 times, 5 hashes. It requires me to do only 1 hash. So no matter how much effort the client put, the server has to do very little effort to verify. So it is proof of work in the sense that it's proving that the client did some work. Let's increase the number of zeros to see that sometimes you need a lot of work. So I'm doing 8 zeros, again 8 binary zeros is 2 hexadecimal zeros. So it says not enough trials, increase and try again. So 10 trials are not enough. So let me increase it to 100. It tried 100, it's not enough trials, try again, let me try 1000. So at 130th trial it succeeded. So ACM of hash of ACM 130 starts with 2 hexadecimal zeros, which is 8 binary zeros. So again if I do this 130, then I get the same output. So it is proof of work. So the response R is proof of work in the sense that it proves that the client did some work to get this response. Because it is difficult to predict the output of a hash function, the only thing the client can do is try brute force search. So it proves that the client did this brute force search. So let me switch back to my slides. So any questions so far? Okay, so the question was that in the blockchain, why are there many block headers? So each block will have information about, each block header will have information about it, the transactions which are included in that block. So as new transactions come in, we have to include some information about those transactions. Okay, so the question was that, the follow-up question is that why can't I just keep adding transactions to the same block? So we will see that to understand why we need blocks, we have to understand mining. So the Bitcoin mining happens on one block at a time, and if we add transactions at the end of the block, we'll have to change the block header, but that would invalidate the mining process. So you need little more context to understand why that is. So we'll keep going. Any other questions? So the question was that does a block have a fixed size? There is a maximum size specified by the Bitcoin protocol. It's about 4 megabytes. So yeah, anything else? Okay. So I told you about this number k, right? So this the integer k, the number of zeros the hash output has to start with. So as k increases, the difficulty of this search process increases. So here I'm trying to illustrate why it increases. So suppose you have a hash function whose output is only 4 bits. Okay, because 256-bit space I cannot represent on a slide. So 4-bit space. So there are 16 possible outputs. So I have listed the 16 possible outputs here. So if k is 1, suppose I want the output to start with 1, 0, then half of the space is allowed. If you see this line here, so k equals 1 corresponds to 8 out of the 16 outputs. If k is 2, then only 1/4 of the space is allowed, and if k is 3, only 1/8 of the space is allowed. So as k increases, the difficulty of searching for this response increases. So in general, if your hash function has n bit output length, like 256 in the case of sharp 256, let's say n is 256, then k is the number of zeros you want your response to start with, then the probability of success in a single trial is 1 over 2 raised to k. So as k increases, the probability becomes lower and lower, and it becomes a harder problem. And that brings us to Bitcoin mining. So mining is the process of adding new blocks to the blockchain. And so nodes who want to perform transactions, they will broadcast them into the Bitcoin network. And the miners will collect some of these transactions into a candidate block. So miners are also nodes. They are special nodes in the sense that they participate in this Bitcoin mining process which I am about to describe. So they will collect some of these transactions into a candidate block. And they will, so this is a candidate, excuse me, this is a candidate block. It's not yet a block on the blockchain. They have to do some work before it can be added to the blockchain. So the candidate block will have a block header. It will specify a number of transactions in the block. Then there is a special transaction called a coin-based transaction, which I will describe later. And then there are a bunch of regular transactions. And this block header will have the version number, the hash of the previous block header. So this, the block header, when I create this candidate block, I need to know the hash of the previous block header. In the linear list, what is the latest block? I need to know its block header. And then there is a hash of the transactions which are in this candidate block. So these regular transactions, I'm going to hash all of these. I hash all the coin-based transaction as well. I hash all of these and I put the hash of that here. And then there are some other fields which we will ignore for now. Now there is actually we should not ignore the threshold field. So this threshold field here, it will encode a 32 byte, that is a 256 bit value, which starts with a bunch of zeros. So an example of this is like here I have shown a value which starts with 16 hexadecimal zeros. So that is 64 binary zeros. So this is the threshold field. It's a 32 byte field which starts with a bunch of zeros. For example, this one which starts with 64 zeros. Now the remaining part can be some non-zero value. So it can be anything. Here because it is 32 bytes, there are 64 hexadecimal digits. So there are 48, I have put some 48 non-zero digits here. So the miner, so the rule in Bitcoin mining is that, so the miner who can find a nonce value, this value here, such that the double SHA-256 hash of this whole block header falls below the threshold, can add a new block. So I'll just repeat that. So who can add a new block to the blockchain? Anyone who can find a response like that R in the hashcash protocol, a nonce value, such that when I hash this double SHA-256 hash this block header, that should fall below the threshold. And as we saw, if the number of zeros in front of the threshold is large, then this probability of finding some nonce in a single trial is low, 1 over 2 raised to k, where k is the number of zeros. So typically miners have to keep trying many times before they can find a nonce value for which this will succeed. And mining is hard because suppose I start with a single zero, that is for the hexadecimal digit in the front is 7, this starts only with a single zero, then the fraction of all SHA-256 outputs, or SHA double, D stands for double SHA-256, the fraction of outputs which fall below this threshold is 1 by 2. So within 2 trials I can find one output on the average. But suppose it starts with 4 zeros, if the threshold starts with 4 zeros, then the probability of success in a single trial is 1 over 16. So this is a Bernoulli random process, so on the average 16 times you can hash and find an output. Now if it starts with 16 hexadecimal zeros, then the probability is 1 over 2 raised to 64. So mining is hard because the threshold value in Bitcoin, the number of zeros in front of that threshold is very large. I'll show you some real world values soon. So the probability, now the SHA-256 or the double SHA-256 output is not uniformly distributed because we don't know the actual distribution of the SHA-256 outputs, but it can be approximated by uniform distribution. So on the average, whatever your threshold value is, the probability of success in a single trial is that threshold value plus 1 by 2 raised to 256. This plus 1 is because when the threshold is 0, there's one value which succeeds, so we need that extra plus 1. I put an approximate here because if the double SHA-256 was actually uniformly distributed in the whole space, then this would be equal, but it is approximately uniform. Nobody knows the actual distribution, but we'll assume it's uniform. So this is the probability of success. So mining is a hard problem, but why should anyone mine blocks? It seems like a hard problem, but what is the incentive? So the successful miner gets rewarded in Bitcoin. So mining is the only way in which new Bitcoins are created in the Bitcoin protocol. So every block contains the coin-based transaction. I told you there is a first transaction in the list of transactions called the coin-based transaction that creates 6.25 Bitcoins. So today the value of a Bitcoin is, I think, around $16,000. So it's about $100,000 worth of money there. So if you can become a miner and you can find a block, then you stand to earn $100,000. And each miner will specify his own address as the destination of the new coins. So new coins are created, but where should they go? Who should own them? The miner should own them. But what does ownership mean in the Bitcoin protocol? Those coins have to be sent to something called an address. I'll describe the address later. And each miner is competing to solve their own proof of work puzzle. Why are they competing to solve their own proof of work puzzle? Because the candidate block, you're hashing the block header. The block header has the hash of the transactions, and every miner will put their own address. So the hash of the transactions will be different for each miner. So they are not trying to solve the same problem. So the block header, the prefix before the nonce, the pre-nonce part of the block header is different for each miner. So each of them is trying to solve their own proof of work puzzle. And miners also collect transaction fees in the block which they create. So this is a lucrative process. So how does it look? So this looks like this. So you have this. So what I'm showing here is that this is not one picture. This is actually split. So these are called mining rigs. This is actually the fan. This is the back of the mining rig. So they'll have multiple ASICs inside. So this is a mining farm. You notice that these people are all wearing, even though they're indoors, they're wearing like winter clothes, because all these mining rigs produce a lot of heat. So you need to have a lot of cooling infrastructure in place. So this is all like air conditioning equipment and so on. So this is like you'll have data centers full of these mining rigs, and each mining rig will have dozens of mining chips. So there are application specific integrated circuits, ASICs, for Bitcoin, which will mine this Bitcoin. And each chip will have dozens of SHA-256 mining cores, because we have to do the double SHA-256 hash, right? So we have each chip will have multiple of those cores. So it is like mining is very competitive, and you cannot do it on your laptop anymore. In the early days of Bitcoin, you could do it on your laptop. And typically these mining farms are located in places with cheap power and cooling, so that they can have so the operating cost of a mining farm will be lower in these places where power is cheaper and cooling costs are cheaper. Okay, any questions about the mining part? So the question was, what is a mining chip? A mining chip is an integrated circuit which will compute SHA-256 hashes. So I could, so it is much more specific than a graphic card. So the comment was that, is this a graphic card? So a GPU can do many other things in addition to, it can do mining also, but it can do many other things. But then you'll be wasting a lot of chip area on doing those other things. Let's say controlling a monitor, showing display, and so on. But a mining chip does only one thing, which is all the chip area is used only for doing SHA-256 computation and nothing else. So the question was that, does every miner have their own proof of work puzzle? Is that the question? So let me just go back to this part here. So this is the mining problem. So you have to hash the block header such that it falls below the threshold, right? Now each miner will put their own address in the Coinbase transaction, because they don't want to give the other miner their money. They'll put their own address in the Coinbase transaction. So the addresses are different. So this Coinbase transaction will be hashed, and the hash of that will appear here. So the hash of transactions will be different for every miner. So the challenge part of the mining process is this: the C in the hash cache would be that these first 5 fields, and the R would be the response. So the C is different for every miner. That's what I mean when I say each miner is solving their own proof of work puzzle. Okay. Yeah, go ahead. So the question was, is mining some kind of cheating because we are not adding transactions? So the thing is, regular people will be broadcasting transactions on the blockchain. Like you and I want to send Bitcoin to my friend. Now the miner is a third party who's helping me maintain the blockchain or is helping me do the transaction. So I will be paying the miner some transaction fees for the service. So it is like a service provided by the miner. So the miner is not interested in doing these regular transactions. The miner is only interested in gaining Bitcoin. So even if there are no regular transactions, the miner will still do mining, and there are many blocks in the Bitcoin blockchain which are empty. They only have the coin-based transaction and there is no regular transaction. Because Bitcoin was not popular all the time. In the early days, there was no transactions happening. Okay. Yeah. So the question was, what is the motivation behind this mining? So I said that, okay, you have public blockchain, you want anyone to add to it, but you need to have some kind of gatekeeping. So if everybody is allowed to add blocks, then it will be full of some kind of spam. So I want to gatekeep, like create some kind of hard problem that, okay, only people who can solve this hard problem can add blocks.
That's true, but then we're wasting a lot of energy there.
Yeah. So the comment was that we are wasting a lot of energy. That's true. Like Bitcoin mining has come under a lot of fire. Say that again.
So what is the useful task there? Yes, it is varying from staking, but then are we doing something useful here?
No, there is no usefulness. So that is why Bitcoin has been criticized for being so much, damaging to the environment. So there is no escaping that. And anyone who says that it's fine because it's a decentralized money, it's called greenwashing. Bitcoin mining is wasteful. There's no question about that. But the utility which has come out of it is that you have for the first time a decentralized form of currency. And this was the first attempt, but later we will see that there have been other attempts where without the environmental impact you can have cryptocurrencies like proof of stake currency. Yeah. Mm-hmm.
So will Bitcoin still be decentralized?
Yeah. So the comment was that is Bitcoin still decentralized if a lot of players accumulate a lot of hashing power? The answer is yes, it is not very decentralized because a certain set of companies have concentrated the hashing power, the total hashing power which is available. So there are a particular set of Bitcoin mining pools. So nowadays people join mining pools where they mine together. So the pool operator has more control than the individual players. So there is still some centralization because only some companies are participating in mining because the capital expenditure and the operating expenditure involved in mining is so large that regular people cannot do it. So it is not decentralized in the sense of the hash power is not decentralized. You are right. Okay. Thanks. Yeah.
Can we mine any cryptocurrency?
Can we mine any cryptocurrency? No. Some cryptocurrencies don't have mining. So
We need blocks.
we
need blocks.
So the question was, can we mine any cryptocurrency? The cryptocurrency, when they create the protocol, they have to specify that this is the mining algorithm and this is the way this is allowed in the protocol. So if it is not specified in the protocol, then there won't be any mining. Like there are many cryptocurrencies which don't have mining. They have some proof of stake kind of algorithm for reaching consensus. I have not come to consensus yet. So maybe we'll pause the questions for a bit and I'll take some later in the break maybe. Where were we? Okay, here. So the block addition workflow is like this. So the nodes will broadcast transactions. So regular people will be broadcasting transactions and miners will accept valid transactions and reject invalid ones. So this solves the double spending problem. So suppose Alice is trying to do some double spending. Now the miner includes her double spending transaction in his block, then and if he successfully mines that block, the other nodes in the network will reject his block because his block contains an invalid transaction. If the other nodes reject his block, he won't get that 6.25 bitcoins. So the miner has a lot of incentive to make sure that all the transactions in the new block he's proposing are correct. If he includes an invalid transaction in his block, then he won't get that 6.25 bitcoins. So he stands to lose a lot of money. So he will make sure that every transaction which is including in the candidate block before starting mining is valid. Otherwise, he'll lose a lot of money. So the double spending problem is solved by having each miner whose incentive or whose main goal is to earn the 6.25 bitcoins, to ensure each miner ensures that the transactions being included in the block are correct. So this is how it look like. So you have, let's say this is the linear list. So suppose the latest block is block B. Then there are a bunch of miners. In this picture I'm showing 3 miners. So each miner creates their own candidate block. This miner has candidate block C1, C2, C3, and they start mining, they start searching for the response. Eventually one of them will succeed, and as soon as suppose C2 succeeded, suppose this guy, this miner was mining on candidate block C2 succeeded. So as soon as this miner has succeeded, he or she wants to tell the world that I have won the race, I have 6.25 bitcoins, now everybody give me those 6.25 bitcoins or start mining on top of my block. So he will immediately broadcast the block he has found with the nonce value to the whole world, so that everybody knows that he has won the race. And then the other miners, they have lost the race for this block, but they don't want to get fall behind in the race to mine the next block. So they will start building on top of this C2. Then there will be again the winning miner also will build, but the other miners also will start building. So then you have candidate blocks D1, D2, D3 who are building on top of this block. So this is the block addition workflow. So the miners are incentive to broadcast the block quickly because they don't want some other miner to win. Suppose they withhold the block, they don't tell anybody about their block. Then some other miner may broadcast their block and say I won the race. So if every second they wait to send their block, they may lose the race by withholding it. So but it can happen that, so a natural question at this point which I have gotten many times, so I preempt that, what if two miners solve the puzzle at the same time? So that is because this is all, nobody is coordinating, right? Every miner is just mining in their own farms, and suppose one guy found a block and somebody else also found a block. So there will be two solutions, it's possible. Then both miners will broadcast their solution on the network, and the Bitcoin protocol, the way it is designed is that nodes will accept the first solution they hear and reject the other solution. So I have here a picture with two miners. Let's say this is miner A, M sub A I have represented it as, and this is miner B. Now both of them found a solution at the same time and they broadcast their block. So the nodes which I have labeled with A, they have accepted this solution, the upper branch solution, as the correct solution, which follows this block N. So and the nodes which I have marked with B, they have accepted this lower branch as the correct blockchain history. So the nodes on this side, the right hand side, they think that this is the linear list, the chain which goes down, and the blocks on this side, they think that the upper branch is the linear list. So then both these parts of both the networks, that the miners on this side will mine on top of this solution A, and the miners on the right hand side will be mining on top of solution B. So eventually one of the chains will get longer, and again the Bitcoin protocol is the nodes will always switch to the chain which is more difficult to produce. So so both the chains will not be growing at the same rate. Eventually one of them will become longer, and then when one of them becomes longer, this was harder to produce because more blocks are in there. So the nodes will always switch to the chain which was more difficult to produce. This is the consensus rule or the Bitcoin protocol rule. So once one of the branches become longer, the other blocks which were created, they become what are called stale blocks. So the Bitcoins created in these blocks are not considered valid. So for this reason, the Coinbase, the newly created Bitcoins, they cannot be spent until they are 100 blocks old. So because this kind of branching can happen, and even though a miner has mined a block successfully, his block may become stale because there is some other branch which was mining faster than him. So Coinbase transaction, the new Bitcoins which are created, they cannot be spent until they are 100 blocks old. So this is the solution to the problem of two miners finding a block at the same time. So eventually the network will converge and achieve consensus. So achieving consensus means that the whole network will agree that a particular linear list of blocks is the correct linear list of blocks, and this is called proof of work consensus. And later in tomorrow you will learn about proof of stake consensus, but this is proof of work. This is so any questions about proof of work consensus?
Address that was also related to proof of work.
Yes. So the question was that each of their miners, when I said each of the miners add their own address, it is also related to proof of work. So when they add their address in the candidate block, in the Coinbase transaction of the candidate block. Yeah. So they specify that if I win this mining process, please send the newly minted Bitcoins to this address. So the question was that if two chains are growing, if there is a fork in the chain, how will the nodes know which is more difficult to calculate? So the simple way you can think of is that the chain which has more number of blocks is more difficult to mine because it has more number of blocks, but there is actually a more complicated algorithm, because that threshold which I mentioned earlier, there is an algorithm to compute the difficulty of a chain using those threshold values. But the simple answer is that the longer chain is the one which is more difficult to calculate. But sometimes it is possible that there are two chains which have the same number of blocks, but there is an algorithm to calculate the difficulty of chain using those threshold values. Basically lower thresholds means harder to compute. So that is the, yeah. Okay. So the question was that at what point do we reject the shorter branch? So the thing is that when nodes receive new blocks, they just broadcast it to everybody in the network. So when a node hears a block, so each of these blocks, because it's a linear list, there is a height associated with a block. So whenever a node hears that it hears of a block with a higher height, then it will immediately reject whatever chain it has. And also if suppose it is the same height, but then it will calculate the difficulty of that and see if it is lower or higher. So every time a new block comes in, typically the block itself is not sent, only the block header is sent, and the block header is enough information to figure out how much that is using the current block header which I have. I see a new block header, then if if it refers to the previous block header, I know the height is only +1, because if you remember the block header had the hash previous block. And then the block also has a difficulty, that threshold. So using that threshold it can compute the difficulty also. So using only the block header it can figure out if the chain it is hearing or the fork which is hearing is harder to calculate or not. Yeah. Yeah. So the question was that this branching happens only when there is a tie and it is some kind of a first come first serve process. Yeah. So if two miners don't solve the puzzle at the same time, it may be possible that a miner solves a puzzle and he broadcasts and all the other miners have been still mining. So then they'll drop their current blocks and they'll start mining on top of that block.